Okay, so our first question is students are given a small sphere, a stopwatch, and a meter stick and are asked to take measurements to create a graph that could be used to determine the acceleration due to gravity. And part A is to describe a procedure for collecting data that can be graphed to determine the acceleration due to gravity. Students have access to a sphere, stopwatch, and a meter stick, and we need to take any steps necessary to reduce experimental uncertainty. So, we would start off our experiment by using putting the meter stick in a spot that won't let it move so we can get consistent readings. Our second step would be to drop the ball from a height of 100 centimeters. And our third step would be to start the stopwatch when the ball is dropped and stop it when it hits the ground. And for our fourth step, to reduce experimental uncertainty, we would need to repeat steps 2 and 3 at least 5 times, get an accurate reading. And our fifth step, in order to get a graph, we would need to repeat steps 2 and 3 multiple times with different values, with different height values. And that would be part A of this thing. And for part B, we need to determine how this data could be graphed and how we would analyze this to determine the acceleration due to gravity. And for gravity, we would need to use the equation x equals v0t plus 1/2 at squared. And since the ball is being dropped from the hand, the initial velocity would equal 0, and that would cancel out this part, and we are left with the equation x equals 1/2 at squared. And since we're desired the value is the acceleration, we'd need to isolate it, so we'd divide the entire thing by t squared, and we would have x divided by t squared equals 1/2 a. And we would need to graph this, and since its slope is rise or run, it would be x over t squared. And after graphing this would be resulted in with a linear line. And in order to solve this, we'd have to plug in our slope, which is m, equals 1/2 a. And to solve for a, we'd have to multiply this by 2. So our acceleration would be 2 times our slope. And that concludes part B. And for part C, we have this new table, and we'd have to indicate which measured calculated quantity could be plotted on the y-axis to create a linear graph, and the slope we could use to calculate a value for the angle of the track, and we could use these values or create new values. But for this, we just need the velocity, which is in meters per second, so the vertical would just be the v. And right here we have the graph, and in part 2 of this, we need to plot the data points with the data up here, and then we would need to label the vertical axis, including units. So our y-axis is velocity in meters per second, and we would need to graph this. And since there's 5 boxes here, we'd do 0.2, 0.4, 0.6, 0.8 in 1 second, and then 1, 2, 3, 4, 5, 2, 3, 4, 5, and this box would be 6. And in order to graph this, we'd have at 0.1 seconds, we'd have a velocity of 1 meter per second, so that would be over there. And at 1.7 seconds would have, or at 0.3 seconds would have a velocity of 1.7. So it's be right there. And at 0.5 we'd have a velocity of 3. Be right there. And at 0.7 we'd have a velocity of 3.7. I'll be right there. And at 0.9 seconds, we'd have a velocity of 5. And that was right there. Oops. And that's part 2 of it. And then part 3 is asking us to draw a best fit line for the data graph, and part C, part 2. Or line of best fit line would be something like this. And that concludes part 3. And for part D, it's asking us to calculate an experimental value for theta using the best fit line you drew in figure 1 in part C, part 3. And since we were given v equals g sine theta t, we could write that over here. And, if you see, you could see our graph is actually v over t, and that means if we isolate this part, we could get v over t equals g sine theta, and we could actually find the slope over here, so our slope would equal g sine theta. And in order to find our slope, we need to find 2 points on our line of best fit in order to calculate the slope of the line. So at 0.6, we can see that the y value is 3.4, and that's x1, y1. At actually this will be x2, y2. And at 0.4, we can see that it equals to 2.2. And to find our slope, it'll be y2 minus y1 over x2 minus x1. And that means we have 3.4 minus 2.2 over 0.6 minus 0.4. And that gets us a value of 6. So that means we can substitute this value into the m right here. And that gets us 6 equals g sine theta. And then we need to isolate this part, so we do 6 divided by g equals sine theta. And then we need to get the inverse sine of this, so we'll put theta equals inverse sine 6 divided by g, and g equals gravity, so we could substitute a 10 in there, so we get sine -1. Theta equals sine -1 divided by g, or 10. And if we plug that into the calculator, we get we get 6. It's 0.64 radians, and we'd have to multiply this by 180 pi to convert this back to degrees, and that would get us, we have to multiply by 180 over pi to get us a value of 37 degrees, and that would answer theta for this part, and that would be our experimental value for the best line we drew in figure 1. Thank you.